current mirror consists of 3 PMOS transistors, 1 diode connected and 2 used as current outputs. All transistor has VT is equal to 0.6 voltage, KB prime is equal to 100 microampere per voltage square, and the length is equal to 1 micrometer but 3 different widths, namely 10 micrometer, 20 micrometer and 40 micrometer. When the diode connected transistor is supplied from a 100 microampere source, how many different output currents are available? Repeat with 2 of the transistor diode connected and the third used to provide current output. For each possible input diode combination, give the values of the output currents and of the VSG that results. Okay, so here first they said 1 is diode connected, 2 used as the current output. For that one we had to find out all the output currents. That's the first part of the question. And the second part of the question is asking repeat the same one, but now make it to 2 diode connected transistor and find out the output. And also they are asking us to find out the VSG value for those as well. Okay, now let's see how to do that. Now here we have PMOS. So let's go ahead and draw the circuit for it first. So if you design PMOS, it's gonna look like this. So this is our first PMOS, and for PMOS you will see the arrow going inside the gate, and this is, let's call this one Q1, and there's a current source connected to it that is 100 microampere. That is a reference current, I reference. Okay, and here one is diode connected to acts as a output current outputs. Okay, and okay, and these are current mirror. So you mean these are connected opposite like this. And for okay, yeah. I2, and this one is, let's call this one Q1, this is Q2, and okay, this is I3 and this one is Q3, and this is just for the illustration. Okay, and what we have to find is we have to find out current for each different situation. So first let's see let's see the first situation. So let's say case 1. So in the case 1, what we are going to do is we are going to assume the width of the first one is 10 micrometer. We have different micrometers. We have 10, 20, 40. So each time we are going to assume different width for the first one. So if I assume 10 micrometer for the first one, then I can say W1 is equal to 10 micrometer. And if I take the ratio of this one and this one, that will become I2 over I1 is equal to width 2 over length 2 over width 1 over length 1, and the lengths are equal. It's mentioned right here, length is equal to 1.0 micrometer but 3 different widths. So length is equal for all of them. So it means we can also write this one as W2 over L, W1 over L, length cancels each other, so we will end up getting W2 over W1. And let's go ahead and continue the next page. So from this one, we formed an equation I2 over I1. I2 over I1 is equal to W2 over W1. Okay, so I1 is nothing but the reference current, that is this. So instead of I1, we can also write this as I2 over I reference. Okay, and we assume the first one to be 10 micrometer. Okay, so we assume this one to be 10 micrometer, then second one we can assume it at 20 micrometer. So this is like 20 micrometer over 10 micrometer, and then I reference is given in the question, that's 100 microampere. So I can place that one as well. So I2 over 100 microampere is equal to 20 micrometer over 10 micrometer. So this is like 20 over 10, that's going to be just 2 times 100, that is 200 microampere. Okay, so we form the current to be 200 microampere when the first width is 10, and now we can find out the third one by forming exact same relationship. Like now we can say I3 over I1 is equal to, you can put this equation derive again, like W3 over L3 over W3 over W1 over L1, but the length are equal. Finally you're going to end up having just the width alone. So same thing here. So this one end up having W3 over W1. So we know that I1 is I reference, that's 100 microampere, and W3 is, we assume W2 to be 20, then W3 should be 40 micrometer, and that one divided by 10 micrometer, that is equal to 4 times 100, 400 micrometer. Microampere. Okay, now these are the I2 and I3 current. When we assume the width of the first one to be 10 micrometer, and if you assume the width of the first one to be 20 micrometer, now things are going to be different. So we are going to say that one as a case 2. Okay, so let's say case 2. Now we are assuming W1 is equal to 20 micrometer. Exact same equation, like I2 over I1 is equal to W2 over L2 over W1 over L1, and we know the length are equal, so we can say W2 over L over W1 over L, and length cancels, we will end up getting W2 over W1. And here I2 is equal to, I2 we don't know, I1 is 100 microampere, and here we are assuming W1 to be 20 micrometer, so W2 we had to first take the 10 micrometer, so 10 micrometer divided by 20 micrometer, and then that one gives us I2 to be 1 over 2 times 100 microampere, which is 50 microampere. Okay, now that is I2. For I3 do the same thing. I3 divided by I1 is equal to W3 divided by W1, and therefore I3 becomes, W3 in this case is going to be 40 micrometer divided by W1 is 20 micrometer, multiply that one with 100 microampere. So 40 over 20, that's 2 times 100, so we're going to get let me double check. Yeah, we are gonna end up getting 200 again, 200 microampere, and that's the one we got here as well. Okay, so that is the case 2. Now let's look at the case 3. In the case 3, what we are gonna do is we are gonna assume W1 to be 40 micrometer. So I1 over I2 over I1 becomes W2 over L2 divided by W1 over L1, and since with length are equal, W2 over L over W1 over L cancels, so we will end up getting W2 over W1, and this one forms I2 is equal to I1 is equal to W2 over W1, and I2 over I1 is 100 microampere, and then W2, since we assume the W1 to be 40, then we can take W2 as 10 micrometer, and then W1 is 40 micrometer. So this is like 1 over 4 times 100. That one gives I2 to be 25 microampere. Same thing for I3 over I1. Let me use a different color. Okay, I3 over I1 should be equal to W3 over W1. So I3 should be W3 over W1 times I1, which is, we had 10, 20 and 40. So 20 is the W3 we had to get this time. So 20 micrometer over 40 micrometer times the 100 microampere. So 20 over 40, that's 1 over 2 times 100, that's 50 microampere. Okay, so these are the case 3. We have 3 different cases, and we are getting 4 different currents output. We are getting, some of them are repeated, so we can just mention it as one. So here we are getting 200, 400, and then 50. This 200 already there, so 200, 400, 50, and 25, 50 is already there. So 200, 400, 50 and 25. Let's mention over here. So for the 3 possible cases, 3 possible cases, 4 different output currents are obtained. Thus the output currents are 200 microampere, 400 microampere, 25 microampere, and 50 microampere. Okay, so these are the 4 different output currents. Now that's the first part of the question, when we have 1 diode connected and 2 used as a current outputs. Now we have the second question asking, when the diode connected transistors, okay, when the diode connected transistors, okay, that is the first one, and the second part of the question is asking, repeat with 2 of the transistor diode connected and the third used to provide current output. Okay, and for each possible input diode combination, give the values of the output currents and VSG that results. Okay, so here what we have to do is, we have to do for 2 diode connected and 1 act as a current output, which means now the width is going to be a little bit different. Let's see how it is. So for two diode connected, there's one thing that if you have we combine two with to be find out the width efficient. So let's look at the case one. Let's say part for the differentiation I just put part 2. There's no part 2, but just for the illustration. Case 1, we can mention this as effective channel width for two diode connected transistors bearing widths. There are three different widths. We have 10 micrometer, 20 micrometer, and a 40 micrometer. So they have to combine. We have to combine this one in a three different ways. So first we can combine them as 10 micrometer and 20 micrometer. So if I combine these two with, then W efficient become 10 micrometer plus 20 micrometer, and that is equal to 30 micrometer, and that's going to be the width one. So whatever the width we are using for the reference current is going to be the W efficient. So that's the difference. Okay, now let's go and solve the problem. So if you look at the problem before, it's similar, exactly same like that, but this time we just have one output current. So if we take two with 10 and 20, then the current we are looking at is the third one. We already took the first two. So the ratio we are going to have is I3 over I1, and that is equal to W3 divided by the L3 divided by this time instead of W1 you just put W efficient because you combine two of them as one. So W efficient over L1, and length I equal W3 over L divided by W efficient over L. So LL cancels, you will end up getting W3 over W efficient, and therefore this equation becomes I3 divided by I1 is equal to W3 over W efficient, which is we can put all the values right now. So I3 divided by I1 is 100 microampere, and then W3 is the one we didn't choose. So we choose 10 micrometer, 20 micrometer for the efficient. The one we didn't choose is 40 micrometer. So 40 micrometer divided by the W efficient, that is 30 micrometer, and that one gives us I3 to be 4 over 3 times 100, which is 4 over 3 times 100. Let me calculate that. Okay, 1 second. Yeah, 4 over 3 times 100, that gives us 133.33 microampere. Okay, that is our I3. Okay, that is case 1. We just have the one output and we just calculated. And the case 2, now we have 3 different widths. We took 10 and 20, and we have 10, 20 and 40. So we can combine 10 and 40. Okay, so if we take W efficient to be 10 micrometer and 40 micrometer, then W efficient is 50 micrometer. Then we had to use I2 as current right now. So I2 is the current. We have to find out the output. So I2 divided by I1 should be equal to W2 divided by the L2 divided by W efficient divided by L1, and lengths are equal, so W2 over L over W efficient over L. LL cancels, we will end up getting W2 over W efficient, and therefore I2 over I1 is equal to W2 over W efficient. Let's plug in all the values. I2 divided by I1 is 100 microampere, that's equal to W2, that's 20 micrometer, divided by W efficient, that's 50 micrometer. So this is like 2 over 5 times 100. 100 divided by 5 is 20. 20 times 20, that is 100 divided by 5 is 2. No, 20. Yeah. It's 2 over 5. 100 divided by 5 is 20. 20 times 2, that is 40. So we get I2 to be 40 microampere in this case. But just name it as I3 because they say here repeat the 2 transistors are connected and the third used to provide current output. So whatever the third, we are having the length for it as the one we didn't use. So we have to, it's better to choose as W3. Okay, W3 and then I3. This I3 becomes 40 microampere. Okay. So now that is second case. Now let's look at the third case. Case 3. We have chosen 10 and 20. We have also chosen 10 and 40. The only thing that's missing is 20 and 40. So let's choose that. W efficient is equal to 20 micrometer plus 40 micrometer. So that's going to become 60 micrometer right here. And again, same equation. Now I3 divided by I1 is equal to W3 over L3 divided by W efficient over L1, and the lengths are equal, so W3 over L is equal to W efficient over L, which is equal to W3 over W efficient. Therefore I3 over I1 is equal to W3 over W efficient, and let's plug all the values. I3 over I1 is 100 microampere, so 100 microampere right here. And then W3 is, if we choose 20 and 40, the one left is 10 micrometer, so that's the one comes right here. 10 micrometer divided by 60 micrometer, so this is like 10 over 6, that's 1 over 6 times 100. 1 over 6 times 100, if you calculate, you're going to end up getting 16.8 you will get I3 to be 16.67 microampere. So these are the three currents output. When we use two diode connected, we get 133.3 microampere, we get 40 microampere, and then we get 16.67 microampere. So we can mention that. Okay, so for the above, three possible cases, three different current output currents are obtained. Three different output currents are obtained. Thus the output currents are $40 microampere, 133.33 microampere, and 16.67 microampere. Okay, so these are the output currents. Now let's look at the other question, and we have to find the VSG as well. Now to find out the VSG, since this is a PMOS, the current equation is going to be this: I is equal to half time KB prime. Okay, we can say I reference, so ID. I reference is better. Let's put ID first, then. Yeah, the ID current is equal, given by half times KB prime W over L times V over drive square, but for the P Mosfet it's minus VGS, that's also equivalent to VSG, and minus VT whole square. All the values are available, like this ID is I reference, and then half KP prime is given to us, so we can use that. And then here we are going to use the W efficient in each case, divided by the length time VSG, that's the one we are trying to find, minus V threshold whole square. So the only thing that's going to change each time is the W efficient. We have three W efficient. The first one, in the case 1 we had 30 micrometer, and in the case 2 we had 50 micrometer, and then in the case 3 we had 60 micrometer. We have to just plug them and solve for VSG. Let's do that. So here I reference is 100 microampere, so I just put 100 micro, and then half KP prime is given in the question, that is 100 microampere per voltage square, so this is 100 micro. And W efficient, we have three different W efficient. The first one is 30, so plug that one in, 30 micrometer divided by the length that is given to us, that is 1 micrometer, so put 1 micro right here, and then VSG is the one we are trying to find. V threshold is provided to us, that is 0.6 voltage, plug them right here, square. And since we know all the values, we have to just rearrange and solve for VSG, and if you solve for it, you will end up getting this one. Let me see, what is that? So for the first one, if you place 30 for the W efficient, you will end up getting VSG to be 0.85826 voltage. Okay, this is for when W efficient is 30 micrometer. Now let's try the other one. For W efficient is equal to, the second one is 50 micrometer. Exact same current equation. I reference is equal to half time Kp prime W efficient over L times VSG minus VT square, and I reference is 100 microampere. That is equal to half time Kp prime is 100 microampere per voltage square, so 100 micro again, and then W efficient this time is 50 micrometer divided by length is 1 micrometer, so put that one in, and VSG is what we are trying to solve, and V threshold is provided to us, that is 0.6 voltage, so put that one in right here, square. And if you solve for VSG, the second VSG we end up getting is 0.8 voltage. Okay, do the same thing for the third one. The third one we have is, let me do this in a new page. The third one is for W efficient is 60 micrometer. In that time, I reference is equal to half Kp prime W over L, but this W efficient, W efficient over L times VSG minus VT whole square. I reference is given to us, that's 100 microampere, then half, and then this is Kp prime is 100 microampere per voltage square, so 100 micro again. W efficient this time is 60 micrometer. Just put the micro, and that one divided by 1 micro, and then VSG is what we are trying to find, and the V threshold is 0.6 whole square. Solve for VSG, we will end up getting 0.78248 voltage for this one. Okay, so these are the 3 different VSG for 3 different W efficients. Okay, and that's basically it. That's all the question is asking for, and that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my next video.